Yeah, good afternoon. We'll start in 2 minutes. Huh? Nice to see you. Yeah.
So you are planning to share slides?
That's right. So I've already shared a link in the chat box, which is, so let me start recording this. Yeah, it's recording already. So, you know, this is for the students. You already have a copy of these notes.
Yes.
But for other people, I've shared a link in the chat box. That's to the notes which I will be using for this course of lectures.
Okay, okay.
Hello. So can you all hear me?
Yes. Yeah.
Yeah. So maybe we can start. So welcome to this course on local arithmetic. Can you see me, Supriya?
Yes, yes. Yeah, yeah.
I can't see myself. Somehow.
You have to scroll in the participants.
Let's see. Even if I go to this participants, yeah, so this is in the chat box. Anyway, it doesn't matter. I mean, I don't need to see myself. Yeah, okay. So
maybe you can share the screen and then I will let you know whether we can see the slides.
That's very important. Yeah, so let me first share the screen in which we have the syllabus so that I can discuss what we are going to talk about. So share screen, and this is the one. Can you see it now, Supriya?
Yes, yes, yeah.
You can see the syllabus?
Yes.
Okay, perfect. Yeah, okay, I can also see myself now. So, hello, good afternoon, everybody. Most of you are muted, so it's fine. But if you have any questions in between, you can always unmute yourself and ask questions, right? Okay. So I thought I will begin today with an overview of what we are going to do. So sort of explain what is written in this so-called syllabus. And then maybe we'll start with some generalities today. And the actual course will start from Wednesday, okay, so the after tomorrow. So what does the syllabus say? It says that we'll talk about projective limits. So this is a concept which makes sense in any category. Now, I'm not assuming that you are all familiar with the notion of categories and functors, but it's a very simple notion which is useful in all areas of mathematics. So let me recall it briefly. And everything today is going to be sort of just an overview, not very precise with definitions and exact statements, right? So in that spirit, just as sets consist of elements, categories are some things which consist of two different kind of things. There are things called objects and things called morphisms between objects. So every morphism has a source and a target. Moreover, you are told how to compose two morphisms if the target of the first one is equal to the source of the second one. Finally, these data, I mean, there has to be also an identity morphism for each object. So with the same, with the source, that object, and target also the same object. And these things, these data are supposed to satisfy just two conditions. The one is associativity of composition, and the other one is that the morphism that you're calling identity should actually act as the identity for this composition. So that's a very simple concept, but it's a very, very useful and general concept. Okay. So in any category whatsoever, well, basic examples of categories are, of course, the category of all sets. Now you might say that that's not a set, and that's why a category is not really a set. But look at all sets form a category when I take morphisms between sets to be arbitrary mappings. Similarly, there's the category of all groups. So the objects of this category, as I said, a category has to have objects and morphisms. The objects of the category of groups are all groups. And morphisms are what we usually call homomorphisms of groups, right? It's a map from one group to another group, which takes products to products. So that's the category of groups. Then you have the category of topological spaces. Here the objects are all topological spaces, and morphisms between two topological spaces are just continuous maps. Okay, so that's the notion of a category. Now, somehow, it would be nice for me to be able to see whether you people already know these concepts or they are unfamiliar to you. How do I find out? Can you people sort of write something in the chat box or to tell me whether you know these concepts, or should I go into greater detail? So there's this. Yeah. So hello. Do I assume that you all know what categories are, or shall I? Okay, so I mean, since all of you are muted, I'll just continue with this description of what we plan to do in this course.
Well, sir, there have been some responses in the chat box.
Yeah, but I've lost the chat box. Let me see there if I can find it. Let me see. Where is the chat box now? Yeah, here is. Yeah. This is the participants, but where is the chat box? I've written something in the chat box myself, but somehow I can't find it now. Yeah, so what is the response? Can somebody read it out to me?
So I guess it's kind of mixed, I would say, but there are a fair number of people who would like you to go through the basics, it seems. Or an overview.
Okay. That must be Berinder, I think.
Yes, hello, Professor Dalawat.
Hello, how are you?
Yes, I'm very well, thanks.
Fine, okay. So maybe then I should just give an overview of what we are going to cover. And then we'll start with the basics. Let's see. Okay, so the overview is we'll talk about projective limits. So these make sense in an arbitrary category, right? And I've recalled briefly what a category is. So using this notion of projective limits, we will construct a ring called ZP. Now, in our usual college or university courses, they denote the ring Z modulo PZ by ZP. This is not the notation being used here. Here, ZP is a completely new ring, which you are perhaps not yet familiar with. It's not the quotient of Z modulo the prime ideal generated by the prime P. It's not that ring at all. That's a finite ring. This one is not at all finite. And we will introduce the construction of this ring. Then we'll see how to find roots of polynomials in this ring. So there's a lemma called Hensel's lemma, which allows us to do this. Then we will determine the structure of the multiplicative group of this ring. Okay, so given any ring whatsoever, of course, you have the multiplicative group of that ring. For example, Z has the multiplicative group +1, -1. Similarly, this ring ZP has a group, the invertible elements in this ring form a group called the multiplicative group of this ring, elements of which are sometimes called units. But what is special about this ring is that this group comes with a filtration. So a filtration of a group is a sequence, decreasing sequence of subgroups of that group. Okay, so we'll look at that. And that will also allow us to determine the multiplicative group of the rings Z modulo P to the n Z. Okay. Then we'll come to the field QP, which is just the field of fractions of this ring ZP. And then we will come to this thing called the Hilbert symbol in QP. Okay, so all this, the Hilbert symbol and everything, solves the following problem. Suppose you are given a field K, and yes, was there a question? Did somebody ask something? I can't hear anything. Okay, so can you
Sir,
see?
I think you minimize the screen and go to the Zoom, then you can see the participants' response.
Which screen do I minimize?
Yeah, you are sharing the whole screen actually, sir. The syllabus we are looking.
Can you come over to my office and tell me what to do?
Okay, sir, I'm coming.
Yeah. Okay, so we will just fix this problem and then continue. So I'll stop recording for a moment. Okay, so we'll just wait for a few minutes, huh?
So you can see the chat box, right?
I can't see the chat box. That's the whole problem. It has somehow disappeared.
Can you see the mute button? You can move your cursor little down on your window, on your Zoom window.
Yeah, the mute button is there. Let's mute the audio.
Yes, but so in that line you will see the participants chart, share screen. You shared the screen, right? It just by the side of that, there is a chat box.
Yeah, chat 12. Yeah. Now I have the chat box now.
So you
Give
can
some basic idea about category and functor. Okay.
So, I mean, this is my experience of online teaching this semester. Students prefer to write in the chat box than actually talking to the instructor. I don't know. I am more comfortable talking to the students.
Yeah. Okay. So now I can see the chat box. They can write in the chat box if they wish to. Yeah. Can you all hear me?
Yes.
Yeah.
Yes,
so,
sir.
Yeah. Okay, fine. Very good. So let's continue. I've already explained what a category is, but that's not, I mean, we'll come back to this notion. So let's first give an overview of what this course will try to cover, right? So I was telling you that we will introduce this Hilbert symbol. Now, why is this Hilbert symbol there? That's what I was trying to explain. So suppose you have some field K. Then you would like to understand the finite extensions of this field. That's a very basic problem. That is what one wants to know about. In the finite extensions of Q, for example, are very important, and we would like to understand, classify all of them. So now that might be a very difficult problem in general. So you try to understand, let's say, just the quadratic extensions. Okay, so you take the compositum of all quadratic extensions. And so do you all know what a little bit of Galois theory? So now I'm looking at the chat box. Please tell me whether you know Galois theory or not. Or you have some idea. Yeah, okay.
Yes, sir.
There are quite a few yeses over there. So that's very good. I mean, this is the amount of background which is required for this course. And just a moment. Why can't I see the big Zoom screen thing there?
This is your screen actually.
Yeah, that's there. But that's the only thing I'm seeing now, and nothing else is. Where's the Zoom thing?
So if you click on this,
that's this one, right? Okay, yeah. So I can't see any. I mean, I think maybe this is all it's reduced to and so on. So when I go there, I get this, but. So let's continue. Maybe let's continue like this. Yeah. Okay. So I was saying, whenever you have a field K, you are interested in finding out or classifying, understanding all the finite extensions of this field. That might be a difficult problem. So our first step would be to understand all its quadratic extensions. So let's put them all together, which is to say, let's take the compositum of all quadratic extensions of this given field. So there are two or three questions you might ask about this compositum now. First of all, what is it? I mean, can you give some generators for this compositum? Meaning, can you give generators which generate this extension of your base field? The second question is, what is the Galois group of this compositum over the base field? And the third question is, how does the Galois group act on these generators? Okay, so these are the three basic questions which you can ask for any naturally occurring extension of any given field. Here, our field is this field Q of QP of p-adic numbers, and we would like to understand all its quadratic extensions, and that's where the Hilbert symbol will come in. And the Hilbert symbol encodes the action of the Galois group of the maximal quadratic extension of this field QP. And there's something called local quadratic reciprocity, which we will prove. And that gives you a sort of complete understanding of the quadratic extensions of these fields QP. Okay. So that's the first thing. And then, so we will study these fields QP for quite a few lectures. Next, there happen to be another family of fields which are very similar in their arithmetic properties to these fields QP. So these are the fields K par series T, where K is a finite field. Okay, so these are also called, the QPs are called local fields, and so are these ones. QPs are local fields of characteristic 0, and these are local fields of characteristic P. So they also, as I said, the arithmetic of these fields of local fields of characteristic P is very similar to the arithmetic of these fields QP. So there's the Hilbert symbol in this situation as well. And we will determine all the quadratic extensions of these fields. Then we'll come to these general notions of valuations, and when are two valuations equivalent? What is the completion of a field with respect to some valuation? How can you extend a valuation to a finite extension of the field? What are rings of integers in these valued fields? Then there's this notion of residual degree and ramification index, etc. Right? So this will be a sort of general theory of valued fields. These are fields which have valuation, and that controls quite a bit of the arithmetic of the field, especially the ones which are complete for this valuation. Okay, then there's this notion of ramification in an extension of valued fields. So let's just stick to QP that comes with a natural valuation, and an extension of QP will have a natural extension of the p-adic valuation on QP. Okay, so you have these two valued fields, and there's this notion of being ramified or being unramified. So that's a very important notion, and the ramification also comes in two variants. There's this thing called tame ramification and wild ramification. So tame ramification is sort of easier to understand. So we will classify, in fact, all tamely ramified extensions of fields like QP and K par series T and so on. Okay. These wildly ramified extensions are somewhat more difficult to understand, and we will come to them later. Okay, and this ramification is actually something which gives you a filtration of the Galois group of a Galois extension of this kind of fields. So we will study this filtration and how it behaves with respect to passage to a subgroup or to a quotient group. Okay. Then, so there's Hassaya Theorem, which says that the so-called breaks in the ramification occur at integers and so on. Then we'll talk about cyclotomic extensions. And there's this local version of what is called the Chronicle Weber theorem, which says that for QP, all abelian extensions are contained in the cyclotomic extension, right? Then we'll sort of speak about the norm map and, okay, so local Chronicle-Weber theorem is mentioned here already. Then we'll talk about abelian extensions of exponent P, and we'll also try to classify all degree P extensions of fields like QP. right? So these extensions need not be cyclic. So all extensions, and if time permits, we'll prove Serre's mass formula in this case. Okay, so let me stop sharing this. Okay, so now I get back this other window. So in the chat box, please tell me whether you have any questions about this syllabus or what we are planning to do. You are not expected to understand everything that I have said, of course, because that's what we are going to do. But if you have any questions about the syllabus, let me have them here now. Okay, so there are no questions. And I'll now share a different screen. So Priya.
Yeah.
What happens is when I share the screen, the main Zoom window disappears and only the screen that I'm sharing is visible. So when I stop sharing that screen,
yes,
this Zoom window has come back into life. That's what has happened.
Yes, but that's typically is the whatever is on the when you share the screen, whatever is on your desktop, the screen that you are sharing, that only screen will be visible. But we all can see you. I mean, your window, your square of video is visible,
right,
and all participants' windows are also visible.
Okay, that's good. So now I'll share this other screen. Tell me whether you see it now.
Yeah. So there are also some questions in the
yes.
chat.
Okay. What is the question? Where is it gone? So I have to stop sharing in order to see what the. Yeah. Will you some part of local class field theory? Yeah. Okay. So that's a question. Now, you see, local class field theory is the study of all abelian extensions of these local fields, and yes, we will do. Let's say a baby version of local class field theory. So when I said that we will classify all quadratic extensions and what the Galois group is and how it acts upon the generators of this maximal abelian extension of exponent 2, that is a part of local class field theory, but it goes beyond local class field theory. It goes beyond in the sense that it tells you how the Galois group acts. So this is what is called explicit local class field theory. So similarly, we will try to do local class field theory, not for all abelian extensions, but for abelian extensions of exponent p. But we will try to do it more deeply in the sense that we will give the explicit action of the Galois group on the generators of this abelian extension of exponent p. Because what local class field theory does is just tells you what the Galois group is. To say how the Galois group acts on the generators is part of explicit class field theory. So the short answer to your question, Mr. Bhatia, right, is yes, we will do a bit of some part of local class field theory, but we will do it more deeply than is usually understood in classes on local class field theory. Okay, so let me come back to sharing. Yeah, Supriya, yeah.
So they are asking about references or the books to follow.
Yeah, okay, so first of all, has everybody got the link to the notes which I had shared in the chat box right at the beginning? Let me get a response, yes or no. Do you
yes.
people?
Yes, sir.
Yeah. So that's going to be, of course, the main sort of reference. Other references, yeah?
I didn't get that link. Maybe I joined a bit later. I think people who...
Okay, so I'll just...
Yeah, not everyone has it.
I'll just copy it again. Let me see. Did you get it now? It's a link to a Google Drive file, PDF file. of the nodes.
Was it shared on this chat window?
Yes. Also maybe.
We can't see it.
Oh, okay. Okay. I understand why you can't see it. So let me see. Just a moment. Wait, please wait a moment. Can you see? Oh, goodness. Yeah, now I went to somebody else. I said everyone. Now it's going to everyone.
Yes, yes, we can see it. We can see it.
Now it's okay. Okay. Can you see it now? Okay, so fine. So let's start with the rest of the lecture. We have spent about half an hour trying to give an overview of the course. Yes?
There is one more question
in
the chat box. Is there an analog of Hilbert symbol for higher degree extensions? For example, cubic.
Cubic extensions. Well, you see, what you have is, and so the answer is yes. In a suitable sense, what you have is, that's exactly what I meant by explicit class field theory. So Hilbert symbol is explicit class field theory for abelian extensions of exponent dividing 2. And similarly, you can have, so we will come to it. Yes, the answer is yes, there is something. Okay. So shall I now share the other screen and go on to our thing? So what is it that I want to share? Yeah. So can you see this thing which says lecture 0, limits and colimits?
Yes.
Yes, sir.
Yes.
Yeah, okay, okay. So fine. So people who said, let's start with the basics should not be complaining, because I'm really starting at the very beginning. So I more or less said what a category is, but doesn't matter. What is important for us are the categories of groups, or the categories of rings, or the categories of topological spaces, all of which you are familiar with. You might not know why they are categories, but you know groups, rings, spaces. Okay. So let's start with an inverse system of sets, or of groups, or of rings, or of topological spaces. What is it? It is just a family of sets together with mappings Fn from Sn plus 1 to Sn, right? So you, of course, require this. So if it's an inverse system of sets, that's all that is required. If it is an inverse system of groups, then you, of course, want these Sns to be groups, and this mapping Fns to be homomorphisms of groups. If you want it to be an inverse system of rings, these Sns are rings, and the mappings Fns are homomorphisms of rings, and so on, right? So such an inverse system is just denoted S0, and then this F0 mapping from S1 to S0, S2 mapping to S1, and so on, right? This diagram here, can you see the pointer when I point at something?
Yes, sir.
Yeah, okay. So that's the displayed diagram, and an inverse system is a diagram like this, right? So in the language of categories, if you know, the natural numbers also form a category. And what are the objects of the category of natural numbers? They are the natural numbers 0, 1, 2, 3, and so on. And what are the morphisms? There's exactly one morphism from any natural number n to the natural number n plus 1. And of course, they are identity morphisms, but you don't need to specify them because they are there in every category. So you just need to specify morphisms other than the identity morphism. And so you can draw the category of natural numbers like this: 0 going to 1, going to 2, etc. And so an inverse system is just a functor from this category of natural numbers, or rather from the opposite category. So what does opposite mean in a category? So as I said, a category has objects and morphisms, and the morphisms have a source and a target. If for each morphism, you reverse the source and the target, you interchange them, then you get another category called the opposite category of the given category. So for natural numbers, the opposite category is going to consist of 0, 1, 2, so on, but the maps are going to be from n to n minus 1. Okay, so an inverse system can be thought of as a functor from the category of opposite to the category of natural numbers and to a category such as the category of sets or groups or rings or topological spaces. So that's the notion of an inverse system. Okay, so here is a completely sort of trivial example of an inverse system in any category C. So you could take X to be, you take X to be an object of C and declare Sn to be equal to X for every n, and take the map Fn. You see these maps are there between Sn's are these objects of the category. You take them all equal to X, and these Fn's are maps between these objects. You take all of them to be identity maps. That is an inverse system. I mean, it's not a particularly interesting inverse system, but it is an example, just as the empty set is an example of a set and the trivial group is an example of a group. This is an example of an inverse system. Take any object of your category, put that object X in each place, in the 0th place, 1st place, 2nd place, and so on, and take the identity maps between these between these objects. Okay. So here is a more interesting example, and that's a very basic example, as we shall see. You take a commutative ring A, and you take an ideal B in your ring A. Then you take An to be A modulo B to the n, right? So you have just given the objects A1, A0, A1, and so on, but you have to now give morphisms between these objects, which is homomorphisms of rings in this case. So what is the homomorphism Fn from An plus 1 to An? It's the natural homomorphism of rings, which comes from the inclusion of ideals. This M should be a B. Doesn't make, there's no M around. It's B n to the B to the n plus 1 is contained in B to the n. This inclusion of ideals here gives you this morphism of rings. And that's an example of an inverse system. A really special case of this is when you take the ring Z and take B to be the ideal PZ, where P is a fixed prime number. And this example will be very basic in what we are going to do in this course. Okay, so that's the notion of an inverse system. Now you have 2 minutes to ask questions. In that 1 minute, in the chat box, are there any questions? So I'll follow Supriya's strategy and just look at the chat box and not interact directly, not verbally. Are there any questions about what an inverse system is? So there are no questions. Good.
So in that example, so the S0 will be Z only.
Say it again.
In the fifth example, that example that you gave, S0 will be Z. Am I right?
So S0 in this, when A is Z and B is PZ, what is A0? You are asking?
Yes, sir.
So by convention, perhaps B to the power 0 should be equal to Z, right? So A0 is going to be Z by PZ to the power Z. So that's a unit ideal. So it's going to be the trivial ring.
Okay, sir. Okay, sir.
So in this example, which will be of importance in our course, you have the trivial ring here, then Z mod PZ here. We have fixed a prime number P. So you have the trivial ring S0, then S1 is Z mod PZ, S2 is Z mod P squared Z, and F1 is the map from Z mod P squared Z to Z mod Z, PZ, which is the reduction modulo P, and so on. Okay?
Got it, sir. Yeah.
Right. So now let's come to a morphism of inverse systems. So it's better to explain it in this diagram. Here, look at the diagram at the top of the page. So you have one inverse system, S0, S1, S2, S3, and so on. You have another inverse system, T0, T1, T2, T3, and so on. Of course, both these inverse systems have to be inverse systems of the same kind of objects, inverse systems of sets or groups or rings or topological spaces or anything as the case may be. So basically the SIs and the TIs should be the same kind of objects. So if you have two such inverse systems, the one at the top and the one at the bottom, a morphism from the inverse system at the top to the inverse system at the bottom is a morphism, is actually a family of morphisms, gamma naught, gamma 1, gamma 2, gamma 3, and so on, where these are all homomorphisms, and where the squares that you see, they all need to commute. Now, for a square to commute, what it means is, if I start at S1, if I take an element X in S1, apply F0 to it, and then apply gamma naught to it, I get an element of T0, right? The element gamma naught of F0 of X. But I also get an element of T0 by first applying gamma 1 to that X and then applying G0. So that element is G0 of gamma 1 of X. The commutativity of the square means that these two elements are the same. Gamma naught F0 of X is the same as gamma naught, no, this is G0 of gamma 1 of X. So not only should the first square commute, all the squares should commute. That's when you say that this is a morphism of inverse systems.
So indexing set is always the set of natural numbers?
Well, not really. So
because when you define inverse system, you are taking n in natural numbers. In seventh also, n is in natural numbers.
Right.
So
that's right. Yes. So this is a very valid question. And the answer is, I'm doing it in the specific case of natural numbers, but this is a more general notion. You can define an inverse system whenever you have an ordered set. And in my case, I'm taking the ordered set to be the set of natural numbers with its natural order.
Yes.
So this is a special case, but that's the only case which I need for the time being. So I'm explaining it in this specific case.
Yeah, sure.
Right? But there's a more general notion. Actually, maybe I hinted somewhere that there's a more general notion involving not just an ordered set, but actually you can take any category and a functor from that category to your category C, and one can talk of diagrams which are just this kind of functors, and you can talk of the limit and the co-limit of a diagram. So this is a very special case of a very general categorical notion, right? But we just need this special case where our objects are indexed by natural numbers. So that, okay. So in any case, let's understand this notion better. So I have now defined what is meant by a morphism of inverse systems. So for example, I had this trivial example of an inverse system. Did I give it a name, iota x? Yes, here it was. I said you choose an object x of your category and take every Sn to be equal to x and every Fn to be the identity map. And that inverse system is going to be called iota x. So just as that one is a trivial example of an inverse system, here is a trivial example of a morphism of inverse systems. You take any morphism in your category C, then you know that trivial inverse system in which each of these is equal to x and each of the bottom ones is equal to y and each of the vertical arrows is equal to u, that of course is an example of a morphism of inverse systems, right? If all the vertical arrows are equal to this arrow u, all these s's are equal to x and all these t's are equal to y, and all these f's are equal to identity, all these g's are equal to the identity of y. Then of course this is a trivial, this is an example of a morphism of inverse systems. And what is also true is that, of course, if I take the identity map from, if I take the bottom inverse system to be the same as the top one, and I take the identity map between them, that's a morphism of inverse systems. And it's also clear that if I have a third inverse system, ST, and let's call it U, U0, U1, U2, U3, and so on, and the mappings are called H0, H1, H2, and so on. And if I have a morphism delta from the T's to the U's, so there'll be delta naught here, delta 1, delta 2, and so on. Then when I take the composite from S0 to U0, from S1 to U1, from S2 to U2, and so on, this composite is also going to be a morphism of inverse systems from, of course, the inverse system S to the inverse system U, right? So all this is there to say that inverse systems form a category. Of course, the category C being fixed, you fix a category C and you look at all inverse systems of objects of C. These inverse systems themselves form a category because I've defined the notion of morphisms of inverse systems. Okay. So now we come to this notion of a cone over an inverse system. So suppose I'm given an inverse system S, the one at the bottom here. So the S's are objects of some category C. To fix ideas, let's think of these S's as being rings. So the inverse system at the bottom is an inverse system of rings. What is a cone over such an inverse system? It's actually it's just a morphism from this inverse system at the top. Remember, that was the my example of a trivial inverse system where I have the same object and just the identity maps between that object. So C is some ring, commutative ring. The S's are also commutative rings, but these F's are morphisms of commutative rings. And so a cone over the inverse system SIs is just a morphism from this sort of trivial inverse system to the given inverse system. That's what a cone over this inverse system is. It's a morphism. All these squares commute. Okay. Okay, so now it's going to be difficult to read the chats at the same time. So okay, so if somebody is asking whether I get the same inverse limit when I omit a few morphisms, a few of the objects at the beginning of the inverse system, the answer is correct. We have not yet defined the notion of the limit of an inverse system, but yes, the point is that yes, we will come to this thing. You don't lose any information if you omit the first few objects, first few terms in an inverse system. Yeah. Okay. Now, right. So I had this notion of morphisms between inverse systems, using which I have defined this notion of a cone over an inverse system. Now I'm going to define the notion of a morphism of cones. This might sound somewhat abstract, but actually it isn't. I mean, just you'll see a cone is a very simple kind of an object, right? I mean, it's the same object repeated all the time with identity maps, except that you are given these maps to your S's. Now, suppose you have two cones over the same inverse system. You have the cone C over the inverse system S and the cone D over the inverse system S, the same inverse system, right? Then a morphism of cones is just a morphism of these objects, C to D, in whichever category you are working in. We decided to work in the category of rings. So these S's are rings and C's and D's are rings. So this phi is just a morphism of rings. But it should have just one property, which is that this, you will get some triangles, right? I mean, if you have a morphism from, C to D, and you have morphisms from C to Sn and D to Sn, then you want all those triangles to commute, which means that gamma n should be equal to delta n composed with phi, the same morphism phi. Okay, that's the notion of a morphism of cones. So from a given category C, we had the category of inverse systems. Now when I fix an inverse system, I have the category of cones over that inverse system. Okay. Is that clear, or are there any questions till now? Because now I'm going to the notion of a limit of an inverse system. Are there any questions about inverse systems, morphisms between them, and cones over inverse systems? So to summarize, given any category, I have this notion of inverse systems in that category, or inverse systems of objects of that category. These inverse systems themselves form a category. When I fix an inverse system in this category, I fix it, and I look at all the cones over this inverse system, they form a category. And this new category of cones may or may not have what is called, is it an initial object or final object that I'm looking for? So the limit of this inverse system is going to be a certain cone over that system, such that there is a unique morphism to every other cone. So it's a C is required to be. So is it C which is the limit? Yeah, C is the limit, right? So let me just repeat what I just said. You have a category C, then you have the category of inverse systems over that category, of objects of that category. You fix an inverse system, then you have the category of cones over that inverse system. If this category of cones has a final object, then it's called the limit of that inverse system. It's a fairly simple notion, right? You have the category of cones over your inverse system and any final object. Now, it may happen that some of you do not know what a final object in a category is. So let me recall what it is. So an initial object in a category is an object from which there's a unique morphism to any other object of the category. So for example, in the category of groups, the trivial group, the zero group, right, or the group which has just one element is an initial object. In the category of sets, the empty set is an initial object because there is a unique map from the empty set to any other set, right? Yes or no? Is there a unique map from the empty set to any other set? I think you all agree, right? Okay, so that's the notion of an initial object. In the category of rings, just think what the initial object in the category of rings is. It's not the zero ring, because the zero ring, there's no map to Z, for example. It is Z which is the initial object in the category of rings. Similarly, there's this notion of a final object in any category whatsoever. It's an object of the category to which there's a unique morphism from any other object. Okay, so in the, let's see, in the category of groups, for example, there is a final object. That's the trivial group, because there is a homomorphism from any group to the trivial group, right? There's a unique morphism from any group to the trivial group. You require not just the existence of a morphism, but uniqueness as well. That's when it's going to be called a final object. So now we have this category of cones over a given inverse system. And if this category has a final object, that's called the limit of this inverse system. Okay? So those of you who feel that all this is too abstract, don't need to worry. It's there only for this lecture. From next time onwards, we are going to do some very concrete things. We are actually going to deal with specific numbers in some sense, not with this kind of generalities, but I thought it might not be a bad idea to begin to situate these notions in a broader context. So here it is, right? Okay, so now if you have the same inverse system Sn, and if you have two limits, so this is just to say that if you have a final object in a category, I mean, not every category has a final object or an initial object for that matter. But if they exist, they are unique. Why are they unique? because let's talk about initial objects, right? So I have two initial objects. What does it mean? There's a unique map. Give them some names, What do you want to call them? Let's call them x1 and x2. These are two objects in some category, and both of them are initial objects in that category. So there's a unique morphism from x1 to any other object and from x2 to any other object. In particular, there's a unique morphism from x1 to x2 and a unique morphism from x2 to x1. So what is the composite x1 going to x2 and coming back to x1? That's a morphism from x1 to x1. But there's only one morphism from x1 to x1, namely the identity morphism. Similarly, when I start at x2 and go to x1 and go back to x2, I get the identity morphism of x2, which is to say that the unique map from x1 to x2 is an isomorphism. Okay, so any two initial objects are canonically isomorphic, and the same reasoning applies to any two final objects. They are canonically isomorphic. Okay, so that was the uniqueness part, but the existence part is what is interesting in any given context. Okay, so here it says that if I'm an inverse system of groups or rings or topological spaces, then that inverse system always has a limit. Okay. Now, so here's a construction of the limit. What you do is you take the product of all those sets. Products exist in these categories, right? Sets, you can take products, groups, you have the product of any family of groups or any family of rings or topological spaces. So inside this product of all these spaces, you take a certain suitable subset or which has the property that, these, when I go down from the product to Sn and to Sn, you just look at those objects, those sort of families. Elements of this product are families of elements, right? An element from S0, an element from S1, an element from S2, and so on. I take only those families which are compatible in the sense that, suppose that family is X0, X1, X2, X3, and so on. When I take X3, it's an element of S3, right? So the element X2 should be the one to which this element in S3 is taken to by the map to the object S2. So the various triangles which are there should commute, and that's what's written here. Okay. So that's the notion of the inverse limit of an inverse system. Okay, so let's stop for a few minutes to see if there are any questions.
Sir, can you please give an example of an inverse limit of an inverse system where it is simple enough?
Yes. Yes. Okay, so I would think that this example here, ZP, should be simple enough. So what you do is you take the inverse system of rings where these rings are, so S0 is the trivial ring, S1 is the ring Z mod PZ. You fix a prime number P first. So S1 is Z mod PZ. S2 is Z mod P squared Z, S3 is Z mod P cubed Z, and so on, right? So the inverse limit of this family will consist of all families of elements of these sets, indexed by the natural numbers. So an element x0 in S0, an element x1 in S1, an element x2 in S2, and so on. But these families are not allowed to be arbitrary. If I allow them to be arbitrary, what I get is the product of these sets, S0, S1, etc., the product of this set. That's not the inverse limit of this family. The inverse limit consists of those families which are compatible with these maps FIs. So the element that I choose in S2 should map under F1 to the element that I have chosen in S1. Okay? So here is how to construct an arbitrary element of the inverse limit of this when S0. So let's not even take the case of Z modulo PZ, P squared Z, etc. Let's take an arbitrary inverse system of rings. So S0 is a ring, S1 is a ring, S2 is a ring, and so on. And I want to specify what elements of the inverse system is going to be a ring. What are the elements of that ring? So an element of the inverse system is obtained by choosing first an element of S0. You choose an arbitrary element of S0. Then you choose an element of S1 which maps to that chosen element. Then you choose an element of S2 which maps to that element, and so on. So families of such elements, they are compatible families. Compatible because whenever I choose an element in Sn, I'll apply Sn plus 1 and apply Fn to it to get an element of Sn, I should get back the element which I had chosen at the Sn stage. At the nth stage, I chose some element. Then at the n plus 1th stage, I should choose an element which maps to that element under Fn, right? So that is the notion of the inverse limit of an inverse system of rings. So this is the basic example. Oh, okay. So here is a simpler. Okay, here comes the example that maybe you'll find somewhat simpler. You take a commutative ring A and look at the polynomial ring in one variable, or just take the polynomial, take all the ring K and take the polynomial ring in one variable T over that commutative ring K. Okay. Now, the polynomial ring, I can form an inverse system out of this polynomial ring by taking S0. Where is S0? Here. I take S0 to be KT modulo T. I take S1, or I mean here it was maybe KT modulo KT, or here take S1 to be KT, the polynomial ring modulo T. S2 to be the polynomial ring modulo T squared. S3 to be the polynomial ring modulo T cubed, and so on. And of course, there are these natural homomorphisms of rings between these rings because these ideals are contained in each other, right? They are powers of the same ideal. So the ideals, the powers get smaller and smaller. They are included in the lower powers. Okay. Now, what is the inverse limit of this system of inverse system of rings? The inverse limit is the ring of formal power series in the same variable t. Okay, so a polynomial, you have the polynomial ring. There are finite expressions in your indeterminate t, right? So they are a0 plus a1t plus a2 t squared and so on, up to some an t to the n. But if I now allow these expressions to go all the way up to infinity, I treat this as a formal kind of expression. It's called a formal power series. So that's the inverse system. That's the inverse limit of this inverse system. Okay, so there's...
Sir?
Yes.
So when you define that inverse, that cone,
yeah.
So that object C is coming from some different category.
No, of course it has to be the same category, because there are these, whereas the cone here, the object C has to be in the same category as the objects SIs, because there are these morphisms from C to the SIs, right? There are morphisms in the same category. Everything is happening in some fixed category. So if the SIs are groups, C is a group. If the SIs are rings, C is a ring. If the SIs are topological spaces, C is a topological space, and so on.
Thanks.
Yeah. Right. So there's some question here. Yeah. So I think the first non-trivial example of an inverse limit should be this: how you get the formal power series ring from the polynomial ring. So the polynomial ring modulo t squared is just essentially polynomials of degree 1. Modulo t cubed, it's essentially polynomials of degree 2. Modulo t to the power 4, it's essentially polynomials of degree 3, and so on. So when you take the inverse limit, what you get are polynomials of arbitrary, not just arbitrarily high degree, but you get infinite formal power series. Okay. So there is this notion, it can be called the dual notion of direct systems. So we had talked about inverse systems. They were, the maps were from S1 to S0, from S2, from Sn plus 1 to Sn. Here the maps are from Sn to Sn plus 1. So this is called a direct system. That's because the arrows go in the same direction as the arrows in the indexing set, which is the set of natural numbers here. And we are thinking of this set as, the arrows going from a number n to the number n plus 1. Yeah, here it is. The n has been thought of as this kind of an ordered set, 0, 1, or even a category, 0, 1, 2, 3, and so on, right? So that's the notion of a direct system. Now, for a direct system, you of course have a similar notion of morphisms of direct systems. It's no different. It's going to be just morphisms like this from one system to another, which make the squares commute. So that's a very natural notion of morphisms of direct systems. But now you have this notion of a cone under the given direct system. Earlier, we had the notion of a cone over an inverse system. Here it is. This diagram, it shows you an inverse system at the bottom, a kind of trivial inverse system at the top, and morphisms from the trivial one to the one that you are interested in, and that's called a cone. But when you are dealing with direct systems, here, S0 to S1 to S2 and so on, that's a direct system. The interesting notion is that of a cone under this direct system. So that it's really this kind of trivial direct system consisting of the same object in all the places and just the identity maps between that object. So a morphism from the given direct system to this trivial direct system is going to be called a cone under this direct system, right? Now, if you have two cones, you have this. So just as there, we had a category, then we have the category of inverse systems of that category. And I fix an inverse system, then I have the category of cones over that inverse system. Similarly, now we have a category, we have the category of direct systems of objects of this category. Then if I fix a direct system, I have the notion of cones, of the category of cones under that direct system, right? So here is an example, here is what a cone under this direct system is. Then you have this notion of morphism of cones, and an initial object in this category of cones over your given direct system is going to be called the colimit of this, or the inductive limit of this direct system. So here is an example, a simple example of the direct limit of things. So let's just take p equal to 2, right? So let's take Sn to be multiples of 1 over p to the n. Oh, okay, well, let's work with an arbitrary prime p, doesn't matter. So take Sn to be multiples of 1 over p to the n. They're multiples inside Q, of course, right? So integral multiples of p to the minus n, that's our Sn. And what is the morphism from Sn to Sn plus 1? Well, multiples of p to the minus n are contained in multiples of p to the minus n plus 1. So there are these inclusions, right? Basically, S1, for example, is a subgroup generated by 1 by p. And S2 is a subgroup generated by 1 by p squared. So p times 1 by p squared is, of course, going to be 1 by p. So the first subgroup is contained in the second one, and so on. So this is an direct system of subgroups of Q. Okay? So Sn is the subgroup of Q generated by p to the minus n, and Sn is p times Sn plus 1. So it's in particular, Sn is contained inside Sn plus 1 for every n, right? Now, the colimit of this direct system is actually a subring. It's the subring Z in which Z to which you adjoin P inverse, and that's a subring of Q. It's basically the union of all these subgroups of Q. Okay. Similarly, that was an inverse system of subgroups of Q, you can take an inverse system of subgroups of Q modulo Z. Q modulo Z is also a group, of course. And you can take Sn to be the subgroup generated by, I mean, the subgroup P to the minus n Z over Z, right? So this inverse system is basically the image of the previous inverse system in Q modulo Z. So this too has a direct limit. Have I been saying inverse system? I mean direct system all the time here, right? All these are direct systems. And you have the direct limit of these things. And in this case, the direct limit, so here the direct limit was ZP inverse, right? When I go modulo Z, the direct limit is going to be something which we will later identify as QP modulo ZP. Okay, so today we discussed some generalities. From next time, we are not going to be dealing with any generalities. We are going to start with some very concrete things. And here is the first one, that's why it's called lecture 1. You have the notes now. You can try to look at them before the lecture next time. But we will define this ring ZP of p-adic integers. Okay, so it's an absolutely useful object in number theory. You cannot do anything today without knowing ZP and some extensions of ZP and so on. In fact, there's a whole school of people working in p-adic arithmetic and various p-adic stuff. Even p-adic analysis is there. So this is what we'll start doing next time. And that's going to be actual concrete things. I thought I'd include the generalities today in order to just place what we will do in a broader context, but they're not going to be strictly necessary for what follows, because we are going to do everything quite concretely. So I'll stop sharing the screen and now ask for questions if you have any.
Sir, will you be sharing the recorded videos also with us?
Yeah, it's getting recorded and it's going to be put up somewhere. Yeah, in due course of time. That's right. But if you have any questions right now, let's discuss some whatever questions you might have. Otherwise, I would like to know, the background of some of the people. This is the first time I'm talking to a computer instead of talking to people. I can't see your faces, and that sort of destabilizes me, because I don't know whether you are following what I'm saying or not following. When the students are there in front of you, you get this visual feedback, which I'm missing right now. And therefore, it would be a good idea to have some feedback and also to know a little bit of your background, so that I can pitch the lectures at the right level, right? So yeah. So does somebody want to say something about their background? Okay, so most of you are students in ICERs. You can write yes or no in the chat box, or you can now unmute yourselves. There's no.
So I'm from ICER.
Yeah.
I'm from ICER coding.
Okay, so you have had courses in number theory, let's say?
Yes, so I had a course in algebraic number theory, a first course where we do basic things.
Okay. Right. So we will not really need much algebraic number theory. We'll only need a little bit of algebra. So groups, rings, fields, Galois theory, that would be more than sufficient for what we will do in this course. Right?
Sir, but I think we will need a localization concept. Concept of localization, algebraic number theory.
Right. You see, so you
because
are right.
when we will study about the completion of QP in ZP etc. So we will need the concept of localization, I think.
You are right. So this QP is a completion of the field Q.
Yes.
Just as the real numbers are a completion of Q, and most people think that that's the only possible completion. Now, about 100 years ago, it was shown that for every prime number P, there's a new completion of Q that was discovered by somebody called Hensel, and this completion is called QP. And many of the things become much easier when you bring in these QPs, right? So these are completions and they're examples of localization, but we will not talk about global things. So we'll not talk about number fields or rings of integers in number fields, and how when you take a prime ideal in the ring of integers, you can complete the ring of integers with respect to that prime ideal. What we will do is, we will first introduce this QP as the completion of Z. Now we'll first introduce the ring ZP as the completion of Z for the p-adic topology. We'll start doing it tomorrow. And then from that point onwards, everything will be in terms of ZP and QP, and in terms of these power series rings. So in characteristic 0, we will not introduce number fields. So you can arrive at extensions of QP in two ways. You either look for extensions of QP, or you look at extensions of Q and then complete them. But we are not going to look at extensions of Q. That's what you would do in a course in algebraic number theory. We are going to remain strictly local. So in fact, from tomorrow onwards, we could fix one prime P for the whole course. You can just fix a prime P, and we'll work with just one prime. Okay. So we'll introduce ZP, QP, and then we'll talk about finite extensions of Z, of QP, and so on. Similarly, these local function fields. So you take some finite field and take the power series ring over that finite field. So how, in what sense, why are they similar to QP? This is what we are going to see in the course of these lectures. They share many properties, but there are some important differences also. And as you can perhaps imagine, the differences are, especially when, let's say, extensions of degree P are concerned. You have this specific prime P which is chosen, right? So even for QP, if you are looking at quadratic extensions, and if your P is different from 2, that's much simpler. If you are looking at cubic extensions of Q2, that's simpler than, or of Q5 or Q7, that's simpler, but cubic extensions of Q3 are complicated. So when there are two primes involved, and when they are the same, things become more complicated than if they are different. So we'll see examples of this. Right. Are there other questions?
Hello? Am I audible?
Yeah, sorry?
Hello, am I audible? Can you hear me?
Yes, yes.
Yeah, sir. I don't really have a very good background in Galois theory. So will I face problems with because of that? I mean, I know a little bit of Galois theory, but not very deep Galois theory.
Right. I think we will not need any deep Galois theory. We will just need the notion of a Galois extension, for example.
Okay.
And that too, we will need it much later in the course. In the first couple of lectures, maybe even 5 or 10 lectures, we will not even need to mention the Galois group at all. Okay, so for quadratic extensions, we might need to mention it, right?
Okay,
but that's not a very difficult concept.
Yeah.
So an arbitrary extension, Galois extension, such things we will come to only towards the middle of the course, because that's when we will talk about the ramification filtration on the Galois group of an extension of local fields. So the answer is no, you don't need to know much about Galois theory. Certainly not the proofs and the statements that we will need. If you don't remember them, you can always ask and we will recall what is being used.
Okay.
So I want to make it a very informal kind of course. And in fact, it's easier for me if people sort of interrupt and ask questions, because otherwise I don't know. I mean, if people are, I mean, I can't see you people, so I don't know whether you are understanding what I'm saying or you are lost. So it would be a good idea to sort of maybe interrupt on the chat box, or even unmuting yourselves and asking questions.
Okay, sir.
Yeah.
Thank you.
Yeah. So are there any other questions?
Sir?
Yes.
Yeah, so I'm really asking this question because you started our course with direct and inverse systems. So will you be defining infinite Galois group for any infinite, like probably the absolute Galois group of Q or QP, something like that? Because I mean, in that case, you need to take the indexing set of your direct system, not just n, but some different partially ordered set. So that's why.
You're absolutely right. Yes. Yes. But yeah, if we need to do it, we'll do it. But I don't think we will need the whole Galois group at some stage. Yeah, if you're absolutely right that if you want to define the absolute Galois group, then you need sort of the more general notion of an inverse system and the inverse limit. But I don't think we will need to do that. Yeah, I don't know. So we will see. I mean, of course, if it's required, then we'll recall it. That's right. But you're right. I mean, it's good that you are familiar with the notion of the absolute Galois group of a field. Yeah. Any other questions? Okay, if not, let's call it quits for today, and we'll meet on Wednesday at 3 o'clock. Okay.